Okay, here, I'm going to share the screen with my iPad now, and we can go to the next step. Very good. So now I'd like to describe the same phenomena, but with equations. So polarization. Once again, the polarization refers to the direction of the electric field vector. For a electromagnetic wave moving in the z direction, the polarization will be a vector that lies in the xy plane, as is shown here. Here, let's write a general equation for this. So suppose our wave has angular frequency omega. Then the total electric field can be written like this. We'll have an x component, and then that should be multiplied by cosine of kz minus omega t. And that component points in the x direction. But there's also a y component. Oops, excuse me 1 second. There we are. Like so. Notice these waves can have different amplitudes, and they can also be offset in phase. Okay? That's the most general case. Oh, and then finally, remember that k is just the same thing as 2 pi divided by the wavelength of the light, and omega is the same thing as 2 pi times the ordinary frequency of the light. Now, for what follows, it'll be convenient if we make one little definition here. I'm going to define theta here as kz minus omega t, just so I don't have to write that over and over again. Then our general state is E equals Ex cosine theta in the x direction plus Ey cosine of theta plus epsilon in the y direction. Now we can look at some special cases. First, the case of linear polarization. For linear polarization, either Ex equals 0 or Ey equals 0, or they can both be non-zero and the phase difference can be 0, or, well, it could also be pi. That would produce the same result. Because in this case, let's suppose that the phase difference is 0, we can write the electric field as Ex in the x direction plus Ey in the y direction times cosine of theta. And you can see that the magnitude of this vector will point in a constant direction from its structure, right? Although the amplitude will oscillate in time because theta is kz minus omega t, and as t increases, the angle will change. So that's the case of linear polarization. The second important case is circular polarization. And here we know from what our investigation just a moment ago that we must have the amplitudes of the x and y components be equal, and we need the phase difference to be pi over 2, or in fact minus pi over 2 would also work. So in this case, the total electric field would be Ex cosine theta in the x direction plus, well, it's the same amplitude, Ex times cosine of theta plus pi over 2 in the y direction. Well, we can rewrite this because cosine of some angle plus pi over 2 is the same as sine of that angle. Then we can write this as EX times cosine of theta in the x direction plus sine of theta in the y direction. And of course, this gives us a vector that has a constant magnitude, which makes an angle theta with the x-axis. And that gives us sufficient to give us circular polarization, because as the time moves forward, the tip of the vector will just trace out a circle in the xy plane. The magnitude or the length of the vector will be constant, and the x and y components will change according to this formula. Circular polarization. Okay, those together with elliptical polarization are the three important polarization states that we need to worry about. Very good. Okay, bye.